The final exam is on Thursday at 10:15, so a week from today you'll be halfway done with the exam. And as for the allowed equation packet you can bring, and then I'll be supplying an equation sheet similar to what I've been giving you in the past. And as I announced last time, the emphasis on the exam is going to be material that's covered since the second midterm, so the emphasis will be on Chapter 7, which is the energy equation, and some of the concepts that we're going to be just getting into a little bit of coverage today in Chapter 8, which is dimensional analysis and similitude. That'll be a greater proportion of the exam questions that you'll get, but then it is a comprehensive exam, so you may see something that requires you to remember what specific gravity is, or you may be required to remember way back when you found a force on a flat surface, or maybe calculated the force required to move two plates that are separated by a thin film of liquid, or something like that. Any questions about the announcement slide here? This is class 28, by the way, and we only have 28 classes from the semester, so it's over. I see a lot of smiles. Those are smiles of pain, right? Frowns. I'll say that they're upside down frowns. Everybody's feeling a little depressed because it's the end of the semester and you're not going to be able to get to do this anymore, but good. All right, I like that. That's perfect. What we're going to be doing today is talking about some concepts from Chapter 8, and Chapter 8 covers a process known as dimensional analysis. Unfortunately, we just don't have a lot of time to cover it in detail, but it's a very useful procedure that allows you to understand how equations are built, or understand the relationship between models and prototypes. So we're going to talk a little bit about that today. The process of dimensional analysis allows you to find out, for example, what dimensions of a model airplane should be used to realistically simulate flight conditions in a wind tunnel. So if you have a wind tunnel and you're going to be trying to design a more efficient wing, you'd go through the dimensional analysis process to find out what wind speed should be used if you've got a small model. You know, this small little wooden model is just an example of the fact that sometimes an enormous full-size airplane would be tested at the smaller scale. So this airplane is landing maybe at about 170 miles an hour. So that's the wind speed over the wing. So if you miniaturize that, and you've now got a small model that you're putting into a wind tunnel, what should the speed of the wind be? You know, if it's a 1 to 8 model, does that mean that you should make the wind go 1/8 the speed? Or should you make the wind go 8 times as fast? Or is it the same speed? You know, how do you get the forces to match up on a proportional basis? And think about a little Matchbox car that they sell at Walmart for about $1. Probably everybody's owned one of those little metal Matchbox cars at one time or another, or at least played with them. Think about if I had one of those and I picked it up and I dropped it from chest height and it falls to the ground, probably nothing's going to happen. It'll be as good as new. You know, it's not going to have the same effect as if you took a full-size vehicle and you dropped it from a proportional height. You know, a little Matchbox car that's 3 inches tall, if I drop it from 5 feet, think about the equivalent height if it was a full-size car. You know, if you lifted up a full-size car with a helicopter and you go up to an elevation of maybe 1,000 feet and then you drop it, what's going to happen to that car? There's not going to be anything left. I mean, it's kind of amazing when you watch Mythbusters. I mean, they'll lift the car by 100 feet and drop it, and there's practically nothing left. It's just a pile of metal and parts. And so the question is, why is it that that small-scale model behaves so differently than the full-size prototype? There's some sort of a discontinuity there in how the model is behaving. And dimensional analysis is a way for us to analyze how things should be scaled so that the model behaves in a way that's consistent with the prototype and how it'll behave. And so you could build a Matchbox car that would crumple and fly apart. You need to make the metal doors much thinner than they are. You know, the problem with the Matchbox car now is it's too strong, right? Because it doesn't fly apart the way that it ought to. So dimensional analysis will allow us to predict how the relationship is between model and prototype. One aspect of this field of study is looking at equations to assess whether they are homogeneous or non-homogeneous. Now, a dimensionally homogeneous equation is when the units on both sides of the equation match up. And ordinarily, what that means, if you have a homogeneous equation, that means that it's somehow fundamental, that the equation is built on the realities of science and the physical world. So take, for example, this equation that's shown on the screen here. This is a Weir equation. We didn't get to play with Weirs in the lab this semester. We'll talk about Weirs next semester. But what a Weir is if you've got a river and then you put in some sort of an obstacle and the water level rises and rises. Eventually the water level will rise and water will flow over the side of that weir. This is a sharp-crested weir. This equation says what flow rate you can expect. What's the flow rate going to be based on how tall is the water, what is h, and how long is the weir, the depth into the page of the weir length, and c is a unitless coefficient of discharge that takes into account turbulent effects, and it's sort of like the discharge coefficient that we used in the orifice equation. So in this equation here, Q, we know from experience, as units of cubic meters per second. That's the left-hand side of that equation. What about the right-hand side of the equation? C is unitless. Length has units of length, obviously, so that'd be meters, for example. So meters. The square root of 2g, that's going to have the square root of g is meters per second squared. So if we take the square root of that, that is meters to the 1/2 power and seconds. And then this last term, h to the 3/2 power, h is a unit of length, and so that would be like meters to the 1.5 power. And so what are the units here? We've got meters to the 1, meters to the 2, 3 per second. So it would be cubic meters per second. So it works out. The units on the left-hand side of the equation are the same as the units on the right-hand side of the equation. So in other words, this equation is not empirical. An empirical equation often is non-homogeneous, and the units aren't the same. So an example of a non-homogeneous equation is Manning's equation. You're going to use this a lot in hydraulic engineering. Manning's equation says that the flow rate is going to be the area, some friction factor, area to wetted perimeter to the 2/3 power, slope to the 1/2. And if you put in the units of this equation, it's not going to be cubic meters per second on the right-hand side like it is on the left. This is an equation that just sort of works out empirically, not by luck, but because what they've done is they've taken some data and they said, well, if we have flow rate and then we have all of the parameters that dictate flow rate. So you'd put the area, the slope, the roughness, and so it's an empirical expression, and dimensional analysis allows us to combine variables together to make equations. It's a process that helps us to see what an equation should be to predict performance. And that's what we'll get at the last of class today, is take a look at the process that is undertaken of analyzing variables to make new equations. Well, let's talk about similitude before we get into that. Here we have a model and a prototype. The model, M, is the smaller device, and the prototype, P, is the bigger device. You can see here this looks like a pair of boats, and they have geometric similitude right now, meaning that their physical dimensions have been scaled down so that the length of the model is, in this case, it looks like maybe half the length of the prototype, And correspondingly, the width of the model is also half of the width of the prototype. And if we looked at it in another dimension, the height of it, everything's been scaled proportionally. That's what geometric similitude is. Now, geometric similitude has that problem that the model is going to be too strong. It's not going to predict the performance of the prototype if we scale the size down, because forces don't scale linearly. And think about the strength of things. It's much easier to snap if you have a stick. A 2-foot-long stick snaps very easily because of its length relative to the cross-section of the stick. And it snaps far more easily than if you have a 1-foot stick. It's not like the 1-foot stick only takes half or double the force to snap it. There's a nonlinear relationship between forces and size, and that's where dynamic similitude comes in. When we're trying to honor dynamic similitude, the idea here is that it's not we want the sizes to be the same. We don't necessarily want to have everything scaled so that the model and the prototype have the same size, but what we're more interested in engineering most of the time is to make it so that the forces are matched, so that there is a scaling of the forces. What's illustrated here is, what if we had a spillway on a dam. So this dam is holding back water. When the water level gets to a certain height, it starts flowing down the face of the front of the dam. This is called the spillway. So if we wanted to go into the lab and build a little model to try and predict how the large size prototype is going to behave, rather than having this model scale on size, what we'd do is we'd try and make it so that the Reynolds number of the model and the prototype match. We'd calculate the Reynolds number, and you remember that Reynolds number is velocity times diameter divided by kinematic viscosity. And that's a way of calculating Reynolds number, or it is mu v d divided by density. Well, I always just write it in terms of this. Kinematic viscosity is absolute viscosity divided by density, so it would be, no, density's on top, right? And the dynamic viscosity on the bottom. So Reynolds number is the key to getting dynamic similitude to match up. The things that we can control in a modeling environment is, let's say that you are going to be testing a wing in a wind tunnel. You could adjust parameters like the velocity of the wind through the wind tunnel, or you could change the fluid. And actually, that's sometimes what they'll do. Rather than having a really fast-moving air, you could increase the density of the fluid that's being tested to water, and then have a slow-moving water. And you could get the same forces acting on a wing with a fast-moving air as a slow-moving water. And so you can adjust a variety of different parameters to maintain the dynamic similitude. You could cool the gas to increase its density, and then that would change the forces as well. And so here's a little calculation example that shows how we can use the Reynolds number similarity in order to ensure that the forces on a model will be the same as the forces on a prototype. Here we have a blimp. The full-size blimp is 60 meters long, and the prototype is 60 meters long and 5 meters wide, and then the model is 1/10 the size of that. And the full-size prototype is going to fly at 10 meters per second, and so if we want to test a 1 to 10 size model in a wind tunnel, what should the wind speed be? And what we're going to do is ensure, in this instance, that the Reynolds number is maintained. That's how we know the correct velocity. And so earlier I asked that question, if you scale it down, does that mean that the velocity will be reduced or the velocity will be increased? And this is what will answer that question. No. Okay, so dynamic similarity means that the Reynolds number of the model should equal the Reynolds number of the prototype. And the Reynolds number can be calculated as the velocity of the model, some length parameter with the model. Now, as I wrote it earlier, I had said that it was diameter. But that's when you're applying the Reynolds number to a pipe. In this case, there isn't necessarily a pipe diameter, but the length parameter that we can use would be either the length of the blimp or the width of it. Anything that's can be used to compare the size of the model and the size of the prototype. And we're going to have the density of the fluid that's used in modeling, and then the viscosity of the fluid that's used with modeling should equal the velocity of the prototype, the length of the prototype, and the density of the prototype. So we've set the Reynolds number of the model equal to the Reynolds number of the prototype. In this example, we're going to use wind or air for both of them. And so that the density of the model is going to equal the density of the prototype. It's air for both. And that also means that the viscosities of both fluids are going to be the same. The wind tunnel that we're going to use for testing will have the same fluid as the blimp is flying through. So what we can do, since those two are the same, is we can cancel out the viscosity term. We can cancel out the density term. The question is, what wind speed should be used in the wind tunnel? The wind tunnel is what the model is going to be flying through. We want to know what's the velocity that should be used with the model. It should be the velocity of the prototype times the length of the prototype divided by the length of the model. So we move this L sub m over to the right-hand side. The prototype will fly at 10 meters per second, and the model is 1/10 scale. So that means that the length of 60 meters for the prototype, 60 meters long, corresponds to the model will have a length of 6 meters long. That's a pretty long model. So we get from that it's 100 meters per second. So remember when we were talking about Matchbox cars, and I said that the Matchbox car is just too strong? That's the problem with it, is it's too strong. Well, this model is going to be too strong as well. If we were trying to find out how the forces may cause the blimp to compress a little bit, because this is a flexible, like a flexible balloon kind of a thing, and as it flies through the air, the wind is going to be blowing on it, and maybe that causes it to deflect and compress a little bit. So if we wanted to understand really how that's going to behave as it flies through the air, we're going to have to be a little bit more forceful with the model than we would be with the prototype. And so what this calculation shows, that the wind velocity should be 100 meters per second to account for the fact that the model otherwise is going to be too strong for it to really be predictive of what's happening with the prototype. So we could do the Matchbox example. If you're going to drop it from a certain height, if the Matchbox is, I don't know, what do you suppose the scale of a Matchbox to a real-size car is? A real-size car is 10 feet long, and a Matchbox car is 2 inches. So that's probably 60 to 1. And so that means that if you drop a car from 1 foot, you'd have to drop the matchbox from 60 feet to achieve the same effective damage. So anyways, any questions about this similitude example with the blimp, or how you go about to set the two Reynolds numbers equal to each other? The kind of exam question that people have typically expected from questions like this would be maybe a conceptual question, asking how do you ensure that you can predict the behavior of a prototype with a model? What is the calculation process? And you just explain, you set the two Reynolds number equal to each other. Or, it's simple enough if I give you a setup like this, just to substitute in the values and calculate the unknown parameter. Here's another one. All right, I'm going to let you do this one independently. We've got oil flowing through a smooth pipe. We know the diameter, we know the viscosity of the oil that's flowing through the pipe, and we know the velocity that the oil goes through the pipe. What if we wanted to model that 15 centimeter pipe? What if we wanted to model its behavior with a 5 centimeter pipe, and it's going to be water instead of oil, 20 degrees Celsius water? So what flow velocity would allow there to be similitude in this case? There's one thing I haven't given you that you need to know. What's the unknown property that you need in order to solve this question? The viscosity for 20 degrees Celsius water. That's right. That's what I haven't told you. Anybody remember what kinematic viscosity of 20 degrees Celsius water is? Good. That's right. 1 times 10 to the minus 6 meters squared per second. All right. So go ahead and try and set that one up, and we'll talk about the answer together. All right. So here we need to rearrange the two Reynolds numbers that are equal to each other, solving for the velocity of the water. That's the question, is how quickly should the water flow through that pipe so that it has similar forces to what the oil pipe is experiencing. Similar forces is what we want to have. And to achieve that, we have the 1 times 10 to the minus 6 meters squared per second as the kinematic viscosity of water, the oil velocity of 2 meters per second, the oil pipe diameter 15 centimeters. The viscosity of the oil is greater than the viscosity of the water. It's 4 times 10 to the minus 6 meters squared per second. The diameter of the water pipe. Turns out it should be 1.5 meters per second for the water to flow through the pipe and exert the same forces as the oil pipe was when the oil was flowing 2 meters per second. So there's a lot of differences there. The viscosity of the oil is greater and the diameter is greater. But the question is, how quick should the water have to move? And it's 1.5 meters. So, any questions with that example? Here we have a diagram of water flowing through an orifice. This is an orifice inside of a pipe. What if water was flowing and actually was going against the intended direction of an interior orifice? Here, in this case, what you can see is that the diameter of the pipe has been restricted by this circular cutout. This would maybe be like a washer inside of a pipe. What if some circular cutout was in there and water was flowing through it, but in this case going the other direction? If we want to find out how this is going to behave, we'd have to go through a process of experimentation. And there are numerical solutions to this. We could do it with a computer to try and predict using something called computational flow dynamics. A computer could try and predict how the energy loss is going to behave, but it's not highly accurate because the turbulence is really hard to model accurately. And most computers wouldn't have the capacity to do enough calculations for a fine enough mesh to predict really what the pressure change or energy loss would be through here. A full-size test, if we're talking about a pipeline such as they have up in Alaska, a very, very large diameter pipeline, and they want to have in a flow restricting orifice, it wouldn't be practical to put it together a full-size test in a lot of cases. So sometimes instead of having a full-size test, they'll have what's known as a pilot study or a bench scale experiment. And so the way to relate a model to a real thing can be with dimensional analysis and trying to predict, to set up a physical experiment that could be performed in the lab that would be able to predict the full-size behavior. Let me see if I still have this video. Sediment scour. Yeah, I do. Good. Okay, this is showing a model. Let me dim the light so you can see it better. This is a computer model of water flowing over the spillway of a dam. This is a dam, and there's a couple of different gates that water can come through and an emergency spillway. So this is showing how sediment is transported through a dam as water flow increases. This is just an illustration of what a meshed model can come up with. And these sorts of models are sort of notorious for having really colorful pictures, and you look at it and you feel, oh, I'm learning a lot about the flow here. If you click on a certain location, sometimes it'll actually give you at that location what is the sediment change at a certain time. So models are nice when you've got the computational power available and can afford the software. But sometimes you don't need to go to all that trouble, and you can use dimensional analysis instead to set up a physical experiment that will be even more accurate than a model would be. So dimensional analysis proceeds with a process of combining variables together that we know have a relationship to the phenomenon that's going to be monitored. So in experimental design, we may need to use Reynolds number as one of the parameters that has to be matched in design. And here's Reynolds number. We've already been using it today in Similitude. And consider the units for each of the components of Reynolds number. I think it's raining. The density has units of mass per length cubed. Velocity is length per time. The viscosity, if you break down the newtons into kilograms meter per second squared, that gives us, when everything's canceled out, a mass term in the numerator, time and length in the denominator. All units eventually can be broken down into three base parameters: mass, length, and time. All units are composed of those three. So what are the units of the Reynolds number? If you put each of these into, combine the density variable, velocity, length, viscosity, Reynolds number itself is unitless, and we already knew that. But this is an illustration of the process that we're going to analyze the units of different variables and combine them in a certain way to try and find out dimensionless pi groups, as they're called. There's something called the Buckingham pi theorem, and your book goes into a lot of detail about the Buckingham pi theorem and how when you have variables influence behavior, you want to rearrange those variables into groups that are unitless. And you'll have a certain number of variables that influence the behavior, and at most there are three numbers of basic dimensions. M at most is 3 because there's length, time, and mass. And so this process of applying the Buckingham pi theorem is just identifying dimensionless groups to try and understand how the variables interact. This is all super abstract for you, and I recognize that. And the best way to make it seem less abstract is just to illustrate it with an example. So consider a marble, some sort of a sphere, that's falling through a fluid. The drag force on a sphere as it falls down through the fluid, the force that's resisting its movement, is a function of how quickly it's moving, the velocity. The drag force will increase with the density of the fluid and the viscosity of the fluid, and also we know that the drag force is a function of diameter. And the question is, what dimensional analysis and the study of Buckingham pi groups can tell us is, what's the equation that relates force, velocity, density, viscosity, and diameter? Like if you were just back in the lab doing lots of experiments, maybe you have different size spheres, and you notice that the drag force changes depending on the size of the sphere. And you notice that the drag force seems to change when you change the fluid because of the viscosity and the density and so on. Well, this process allows us to analyze the variables to find out what is the equation that predicts what the drag force should be. So let's go through that illustration and I'll show you what the Buckingham pi theorem process is like. No, I won't expect you to do the same thing that I'm going to do in the final exam. But I do expect you to understand why we're doing it. Like, what is the objective of this process? And so you don't have to memorize the process or necessarily be able to replicate it, but I do want you to know what we're starting with and why we're doing this and what it comes out with in the end. You know, what's the product of this study? And so let's consider each of these variables. We have force is one of our variables, and it has units of newtons. And a newton is really a kilogram meter per second squared. And so that has units of mass, length per time squared. That is the units of force. Velocity, V, has units of meters per second. And that is mass per time. Not mass, it is length per time. Density has units of kilograms per cubic meter. That's the same as mass per length cubed. Everybody with me so far? We're just looking at what are the units, the fundamental units of each one of these variables that we already know. Maybe just from experience, we know that these variables somehow influence the drag force. And we're going to try and come up with what is the equation for drag force. Viscosity is a Newton second per meter squared. Newton seconds per meter squared, yeah. So this is the absolute viscosity. A Newton, again, is a kilogram meter per second squared. And we already had the seconds from before and the meters squared from before. So if we combine all that together, it's kilograms per second meter. Canceling out the seconds in the numerator and the denominator, the meters there with the meters there. This is what's left, and that has mass, time, and length. And finally, diameter was another thing that from experience we knew that diameter was one of the factors that influences drag force, and it has units of meters, which is to say length. We're going to be combining things together in a table. I'm going to have the variable and then its units in this table. Okay, so I'm going to have a variable of drag force. I'm going to have the variable of velocity, density, absolute viscosity, and diameter. Okay, so for each of these, we're going to write down the variable and its units. Well, I've already got the variable there. The units, for example, of drag force are mass, length, divided by time squared. Velocity is length per time. Density is mass per length cubed. Viscosity is mass divided by length time, and diameter is just length. Okay, now my process, this is like step 1 of a 3-step process. Here in step 2, we're going to again have variable and the units. We're going to combine groups together to try and make them lose their units. Remember how Reynolds number was a dimensionless group? If we combine all the parameters of Reynolds number together, all the units cancel out and Reynolds number itself is unitless. We're going to be combining variables together to get their units to cancel between step 1 and step 2. So for example, in step 1, I'm going to, going from 1 to 2, my strategy is going to be use diameter to simplify units of length. Let me show you what I mean by that. What I mean is I would have force of drag divided by diameter, and then what are the units that are left when I combine that? If I have F sub d divided by d, then that's going to cancel out the length parameter. So all that will be left in the units is mass divided by time squared. So look how that's simpler than the units were before I combined the variables. Before I combined these two variables together, I had mass, length, divided by time squared. Now I've just got mass divided by time squared. So I was able to cancel out the length parameter of the units by combining those two together, by combining the force of drag and the diameter. I could either multiply them together or I could divide them. Those are my two options. Any questions so far? How will I combine velocity and diameter to do the same thing, to try and cancel out the length units? Should it be v times d or v divided by d? Or d divided by v? V divided by d is going to leave me with 1 divided by t for the units. So I had length in the numerator. So if I have v and I divide it by d, then the length term, the length units of d cancels out the length that was in the numerator there, and I'm just left with inverse time as the units for that expression. Okay? How will we combine diameter and density to cancel out length cubed? Multiply. Right. So if we have density times diameter cubed, then all that's left of the units of that combination will be mass. And then with viscosity, I can multiply viscosity and diameter together, and it's mass divided by time. The length parameter is gone. And then I'm just going to leave, this blank because I've sort of used it up. I don't have to combine anything to get rid of the diameter term. Oh, you're looking into the future. Yes, we can do that. We have a couple of different options. There's no one right way to solve these, but one of the options is we're going to want to cancel out the mass term. We've got to get rid of mass and we've got to get rid of time. So in step 2 to 3, as I go from 2 to 3, I'm going to use something to simplify units of mass. In this case, I'm choosing to cancel out mass. I could have, in this step, if I wanted to, I could have canceled out time, but let's do mass first. So I was using d as a tool in the first jump. What should I use as my tool to cancel out mass in the jump from 2 to 3? David, what do you think? What is the combination of variables that will allow me to cancel out mass? What's my tool? All right, it's the density times d cubed is the term that has mass. And so, for example, how can I combine this and that so that there's no more mass term? Well, I'm going to have to divide them. And so the combination of those is going to be the force due to drag divided by the diameter and, let's see, times density, diameter to the third. So it'll be diameter to the fourth and density, and then all that'll be left now will be 1 divided by t squared. This is getting pretty deep into the weeds, right? It's too bad we don't have 2 lectures for this, because it's in the second lecture that I really turn you loose into some of the Buckingham Pi stuff. That's usually a crowd pleaser, so I'm sorry that this is the last class of the semester. All right, so we've canceled out the mass term here. Now there isn't a mass term in this combination, so it just carries through. It's still just v divided by d, and it still has units of 1 divided by t. So we couldn't cancel out a mass term there. And here, we just leave it blank like we did in the last step. But now we're going to need to combine these two together to cancel out the mass term in viscosity times diameter. And the way to do that is going to be viscosity divided by density diameter squared. So what we did was we had viscosity times diameter, and we divide it by density times diameter to the third, and this is what's left over. And the units that are left are 1 divided by t. So that combination was just this divided by that. Last jump from stage 3 to stage 4. We want to eliminate time, and we can use any number of these. We could either use mu, or we could use v to eliminate it. Let's say that let's use v divided by d to simplify units of time. So how do we, if this is the one that we're going to be combining into other things, how do we combine this into there and into there in order to cancel out the time units? Well, here we could say it's the force due to drag, density, velocity squared, diameter squared. So what we did was, since it's t squared, we're going to have to multiply by the inverse of it squared. So d squared goes up in the numerator, v squared is in the denominator. And then that ends up with a dimensionless group. That's our final dimensionless group here. This we leave blank, we're using it elsewhere, we're combining it into other terms. We have to do a similar thing down here. We're going to be multiplying by the inverse in order to get that group combined. And so we end up with viscosity, density, velocity, and diameter, and that is dimensionless. So what was the point of all that? What can we do? All right, what we do now is we know that the force due to drag divided by the density, velocity squared, diameter squared is a function of the viscosity, density, velocity times diameter. Yes? Just that, essentially that they're equal to each other. I could just say that they're equal. And so if we rearrange for f sub d, move the denominator of this expression over here to the numerator, it's going to be viscosity times the density, velocity squared, diameter squared, density, velocity, diameter. So we can cancel out the like units, and we end up with, it is just viscosity, velocity, and diameter. We did. But the question is, which units did we look at? We had to somehow have a feel for what are the parameters that affect the drag force, and then once we know what they are, we can rearrange their units, and this is the equation that we came up with. Now, there is a constant involved there. It turns out, like, if you go and look up what is the drag force for a sphere, the true equation for the drag force of a sphere is 3 pi times the viscosity, diameter, and the velocity that it's falling. And so, that's pretty close to what we had here. It's just that there is the 3 pi constant. So if you're doing experimentations, the 3 pi constant would be obvious pretty quickly. If you're going to be drawing a slope of the line, then that would pop out at you what the constant should be. Well, what do you need to know for the test? You need to know what this process is all about, why we do it, what it gives you in the end, and what is they call this a pi group. And being so close to lunch, even saying it just makes me hungrier. A pi group. These are dimensionless groupings of units. Yeah?
Selecting which variable you're going to use to cancel out in the next step. Does
Yeah.
it always have to come from the previous step? Or
Oh, yeah. So we're in step 3. Should you look at these combinations, or could you go to the... You should look exclusively at the column that's in the previous step. Now, some things will carry through without any change, but you shouldn't go back to the first step because that might lead you to select something that had already been used up, so to speak. Yeah. Well, we've got a minute and 40 seconds left in the semester. I think I'm going to let you out early today, because I'm such a big-hearted guy. Let's just look one last time at the announcements, and we'll be done. Our final exam is Thursday, the 12th at 10:15 a.m. Bring that equation packet that I gave you, the FE equation packet, and then I'm going to supply an additional bonus equation sheet. And if you've got any questions as you prepare for the exam, feel free to stop by my office. I'd be delighted to meet with you, and have a great day.